When we get started, we have, I want to butcher your name, Khazhgali Kozhasov, talking about Riesz kernels.
Okay, thank you. I'm very pleased to be here. Thanks for the invitation. So it's a joint work with Bernd and Mateusz Michalik. It's not yet on archive, but we are working. So, so we say that we will consider a cone, a convex cone, which is open. So I will reserve C for open convex cone in Rn. And I consider a smooth function on this cone that takes only positive values. Okay, and I say that f is completely monotone okay. F is completely monotone, and I will abbreviate it to CM. If I take any vectors from my cone and I take the directional derivatives again with respect to these vectors of my function f, this has to be always a negative function up to this sign, or case any. Okay, and you have seen a definition which looks similar in the talk of Cynthia, but it's not, I don't know like what is the relation between log-concave functions and completely monotone functions, even if the definitions look very similar. So for example, you can think of positive Orson, okay, and then this condition is equivalent to taking all kinds of partial derivatives, and this has to be non-negative on positive Orson. And some examples of functions of this kind are, you can take, for example, f of x to be e to the power minus x. Then the cone here is positive line, okay? And you can easily check that when you take any case derivative of this function, then it will be positive whenever x is positive. And another example is...
Very low.
I think that's it.
Okay, sorry. Okay. Okay. Another example is...
The camera will not...
Okay. You take reciprocal of your variable. This will also be a function on positive Orson, on positive line, and you can also check that when taking derivative, the sign of the derivative just alternate. Okay, and we will be interested in functions that are a very specific type. They will be inverse powers of hyperbolic polynomials. Okay, and in general, for any kind of functions, like it doesn't matter whether f comes from a hyperbolic polynomial or not, there is a beautiful characterization of completely monotone functions that is due to Bernstein, Hausdorff, Lieder, and Jacquet. They didn't write paper together, so it's this are like so.
This is one variable case.
Sorry?
One variable.
Bernstein proved it in one variable, and then I think Jacquet gave like a full generalization to any cones in any dimension. Okay, then theorem says that f defined on C is completely monotone if and only if there exists a Borel measure on on the dual of this cone. So by C star I will denote the closed dual. Okay. So if somebody doesn't know, so this consists of 5 vectors. I will also dualize. I will not dualize. I will identify Rn with its dual, such that scalar product of y with x is always non-negative for any x in my cone C. There exists a measure on this dual cone such that f of x can be represented as e to the power minus yx d mu of y. So by measure on C star, I mean measure that is supported on C star. Okay. And this theorem is very powerful because this condition tells you that infinitely many conditions hold for f. So in particular, for example, when f is the inverse power of a polynomial, you will get infinitely many non-negative polynomials on some C, or for example on positive force. So it's like you cannot check it, right? And this condition guarantees that if you are able to find a measure such that this representation holds, then this infinite series of inequalities hold for f. It's easy to check actually that this is a sufficient condition, because when you apply any kind of derivative, just monomial of in y pops out, and you integrate a positive monomial against positive measure, and you'll get again something positive. And this theorem was, for example, if you take one of these two examples, for example, if f of x is e to the power minus x, then this measure, so the measure has to be supported on the dual of this positive line, which is itself non-negative line, right? And the measure here is just a direct measure that is supported in 1, at point 1. So it's shifted direct measure. So just when you plug in this measure here, you'll get exactly e to the power minus x. And for another function, f of x reciprocal of x, this measure mu is just the back measure on positive orthant. So it's actually easy to check, because x to the power minus 1 is e to the power minus y times x dy, and you integrate from 0 to infinity, and you will have to change your variables. This is actually an identity, so you can easily verify this. Okay, now from now on, P will be a hyperbolic polynomial, which will be always homogeneous. Okay, and I will denote by C, P, or sometimes I will drop P, its hyperbolicity cone. So sometimes, of course, I need to specify, so for most polynomials, of course, there is only one hyperbolicity cone, but when there are two, I need to specify which cone for me is hyperbolic. But I will always assume that P is positive on C because of this definition. So I want to take only positive functions. Okay? And then I'm interested in the following question. When and or if p to the power minus alpha, which is a perfectly defined function that takes positive values on my cone C, is completely monotone. Okay? And in fact, this question was studied. I think like this activity has something to do with another semester that took place here, Riesz, right? Like 4 or 5 years ago. And Bernd, Mateusz, Caroline, and Piotr Cwiernik, they studied this and they wrote a paper. And I will talk about it in the next 5 minutes. Okay, so first of all, if P is not necessarily hyperbolic, it's just a homogeneous polynomial with real coefficients that is completely such that is a homogeneous polynomial such that p to the power minus alpha is completely monotone, then P must be hyperbolic. with respect to C. Okay, and this essentially follows from this integral representation, because if this representation holds for inverse power of P, then in fact you can, it's actually a theorem, but it's not easy, it's not difficult to prove, that the function can be extended analytically to the tube domain, namely to the domain this will be the only proof I'm going to present in my talk. If this inverse power is completely monotone, then there exists a holomorphic function extension of this function of this function on C plus I Rn. So you consider, for example, when C is positive force, this is exactly the domain that appeared in the talk of Josephine, and that restricts to F. Okay, and this is actually, you can check that it's just it is just equivalent. The condition that Josephine gave you for stability is almost the same as the condition for non-vanishing for P on this domain, right? And this is equivalent for homogeneous polynomials to being hyperbolic, because it's like one-line exercise. Okay, and
what's the quantifier on alpha?
Sorry?
What's alpha?
Okay, so if there exists an alpha, and you can check that alpha must be necessarily positive or 0. Okay, if there exists no negative alpha such that this is completely monotone, then you're hyperbolic. Okay, and and how can you check like that such a that this holds for some inverse power of your hyperbolic polynomial? You need to kind of find the way back from your function to possibly to potentially exist in this measure, right? But you don't a priori that this measure exists, because otherwise you would be done. Then there is an inverse operation that out of function transfers something that is not in general a measure, and then we can check whether this is positive or not. And this is an inverse transformation that is called inverse Laplace transform. So in fact, it is a theorem due to Gardning that for any, in fact, complete means that C is pointed, and that's it. Okay. So if your hyperbolicity cone is pointed, then you can go back. You can reverse this procedure and cook up a function. The following function is well defined that I will denote by Q alpha. It will be function on the dual of my cone, and it looks like as follows. So let me check again. So you integrate this function, which is actually a complex valued function, over Rn, where x is my variable, and E is any point in the hyperbolicity cone. Okay? And in fact, you can check that this function, the whole integral takes only real values as a function of y. Okay? And this Q alpha is a perfectly defined, is a continuous actually function. With support, so you don't actually a priori require that Q is only defined on C star, but it will be automatically satisfied with support in C star, such that, and moreover, you can go back to P essentially in the same way as you did it for completely monotone function. So you integrate Q alpha of y dy, which is absolutely continuous function with respect to the back measure on my dual cone. But the problem is this representation defines, of course, my polynomial, hyperbolic polynomial P, but nobody said that this Q alpha is positive, okay? And
So there's some inner product in the exponent in that integral?
so I fix inner product on my, I identify, sorry.
I think what is e to the y times e plus I?
So it's brackets.
No, I mean up in the previous one.
Oh, yeah.
There is, right? There's just,
In
I'm
the
just
line,
making sure.
in the definition of Q alpha.
Above, in the definition of Q.
Oh, yes. Sorry, yes, sorry. By this I mean dot product, okay, sorry. Okay, and, okay, so the four people I mentioned, namely Bernd, Mateusz Karolin, and Piotr Czerny, they conjectured, like 4 or 5 years ago, that there exists an alpha that is sufficiently big. So this condition is actually to ensure that this is a well-defined function, because in general, it might, this integral that defines my Q alpha might not be a well-defined function. Okay? They conjecture that there exists alpha such that Q alpha is always non-negative on C star. Okay? And it's still open, actually. So suppose that one consequence of this conjecture, if it's true, is that every hyperbolic polynomial admits a negative power that is completely monotone. Okay? Because if Q alpha is non-negative, then this representation with this theorem tells you that F is completely monotone on the cone of hyperbolicity. Okay? And in fact, so that's why I say that completely monotone functions can be used, if they come from hyperbolic polynomials, they can be used to construct infinite sequence of non-negative polynomials on your cone. But in general, this conjecture is open, and let me mention what is known about that. Was this conjecture born in this building?
Yes. I think the answer is yes.
Okay. Okay, so known cases, of course, the first case you can think about is a determinantal polynomial, okay? And in this case, it's actually settled, but it's actually even more. So if P, if some power of P admits positive determinantal representation, then there exists alpha that is sufficiently large such that p to the power minus alpha is completely monotone, okay? Or in the same equivalently, Q alpha of y is non-negative on my cone C star. So actually, this so like I will switch from several times from this condition an equivalent condition of being complete monotonicity for this exponent. So if such Q, if this is non-negative, then p to the power minus alpha due to this representation will be completely monotone by this Bernstein-Turquet theorem, and vice versa. If for some sufficiently big alpha this is completely monotone, then Q alpha defined by that formula will be non-negative. Because I forgot to mention that this, so due to uniqueness in this statement, so actually I didn't write unique. There exists a unique Borel measure, which is very important. So this transformation is injective, like from the space of measures that are supported on C star into smooth functions. This is a transformation that breaks measures into smooth functions. This is injective, okay? And moreover, the image of positive measures is exactly completely monotone functions on C. Well, this is a complete description, so just a tautology, okay? And this cases, of course, like it covers a lot of hyperbolic polynomials, okay? And another class of hyperbolic polynomials is, before I write, let me ask the audience, I think the answer should be known, whether elementary symmetric polynomials admit determinantal symmetric representation up to taking high enough power. If the power of elementary symmetric polynomial is known to be determinantal or not. I know that the cones are spectrohedral, but I don't know if they admit actual determinantal representation. What is the answer?
Unknown?
Yes?
Beta.
You know?
Pardon?
Do you know?
If the powers.
Yes, if the powers admit the determinant representation.
Then you wouldn't be giving this talk.
No, it's not. It's not. The purpose of this talk is not to list this case. I don't know. I asked Mario Kumar, and he said he doesn't know.
No, but if so, then you would be able to.
Yes, exactly. That's why I said that before I write something, I want to be sure. Sorry?
Then you would be able to compute the risk count if it was explicit. Right?
Yes, it was. If it was explicit, I would be able to do it.
You want to say that Q is called the Riesz kernel?
Oh, sorry. Oh, sorry. Okay. So, definition, which is actually in the Q alpha is called Riesz kernel. Of P. Okay. So so the answer is not known, right? Okay. So then the second class is a class elementary symmetric polynomials. Okay. And in this case, it's known that the conjecture holds, and you need to take alpha big enough to exhibit such measure, Q alpha, such Riesz kernel, and yeah, and this will appear in a forthcoming preprint. Okay, and that's more or less what is known so far.
So in the first case, how explicit is Q alpha then?
Okay, I will talk about it right now. So Q alpha in the first case, it's actually very interesting. So it has appeared already in statistics paper, and I think people that know a little bit of probability have encountered already this Q alpha in an explicit way. So, so in the first case, we can say, okay, first let me take determinant of A, where I just consider A to be any K by in any matrix in positive definite cone, and the size will be M. Okay, this is my P of A. Then there was a result of Scott and Sokol, which is very beautiful, and it's a complete characterization of exponents for which this function is completely monotone. If and only if alpha is one of the following. It's either half integer, where k is from 0 to m minus 1, or alpha is greater than m minus 1 over 2. Okay, so it's a complete list of exponents for which this function is completely monotone. And moreover, we can write down the Riesz kernel. Okay, and for example, in the first case, let's call this case A and this case B. In the first case, A, the Riesz kernel is given by the following integral representation. Determinant of, what is determinant of A to the power minus k over 2 equals integral over the space. So let me first write you and then I'll explain. Sorry?
It's a Gaussian integral.
It's a Gaussian, exactly. dx, where dx is, so x will be matrix, k by m matrix filled by vectors x1, etc., xk. So it will be run k matrix, okay? Because k is in this range, so it's between 0 and minus 1. And dx is just essentially scaled Lebesgue measure dxj I over square root of pi. So you take entries of this map, so there are k times m many entries, and you just scale each entry by square root of pi. And this is my Lebesgue measure dx. Okay? And you integrate over the space. And in fact, it does not look the same as this formula, because here you see that it's another, so x enters linearly, but linearly here. But here we integrate over, not over the cone of matrices, but we kind of push forward our measure, we will kind of pull back our measure to the set of rank k matrices that are defined by x. So I consider this transformation, this map from x to x times x transpose, and I end up in positive semi-definite cone of size k, of size m, which is dual to positive definite cone. Okay, and then this defines you explicitly the measure we require, because then it's just the measure will be pushed forward of the Lebesgue measure dx through this map. Okay, and in the second case, when exponent is large enough, we can give.
This is like the Wishart distribution.
Yes, this is called Wishart distribution. Exactly. Thank you. This is called. That's why I said that people know probability or statistics, they should recognize it immediately. And in fact, note that this measure is not absolutely continuous. So this Q alpha in this sense does not exist. Because this measure, what is the image of this map? It's the set of matrices of rank at most k, right? So it lives on the boundary of the PSD cone, okay? So as a function, this Q alpha does not exist, but it's indeed a measure, which is positive, of course. And this defines my Riesz measure, or which is not a function, but still it's the measure. Okay, and in the second case, when alpha is at least m minus 1 over 2 or greater, sorry, actually strictly greater, my function admits the following representation. It's up to some constant that I will write later. It's an integral over positive semi-definite cone. So my scalar product here is a trace scalar product or a Frobenius scalar product, if you want. And the measure is given by this expression. So dB here is a product of dBij. So all entries on the diagonal and above. Okay, and the constant m is some ugly constant that is pm to the power plus 1 over 4 times product of gamma functions. Okay, and from okay, and this function is now a well-defined function, so it's a continuous function. You can make sure it's actually a smooth function on the positive semi on the boundary of the positive semi in the interior of the positive semi-definite cone. And in particular, so there is an so what can be said about completely monotone functions in general? So what operation preserve complete monotonicity? Of course, you can multiply to completely monotone functions, and you will get completely monotone function. And you can also restrict to a subspace that intersects your cone. So if you restrict it to a subspace, subcone, okay, then it will be also completely monotone. In particular, and that's why any power. So if P admits a determinantal representation up to taking enough power, then of course, and after taking this power and restricting it to subspace that is given from the determinantal representation, you will get a complete monotonicity. Okay, and one interesting case, which I plan to discuss now, is the product of linear forms. So namely, when P is just a product of m many linear forms. So, particular example. Okay, particular case of a function of this type is when p of x is just product of linear forms. I take m many vectors, Ln, Lm, and I take products of linear forms defined by these vectors. And of course, in fact, in this case, it's not only completely monotone for exponents in this set, but it's actually completely monotone, the inverse power of this alpha's inverse power, so it is completely monotone for any positive alpha. Because, so, and you could already observe it from the example of a completely monotone function I gave you on the first board. So if you take f of x to be x to the power minus 1, this is completely monotone, right? But in here, I can take any alpha, and it will be still completely monotone for any positive alpha, right? In particular, so it's easy to get to complete monotonicity of for one linear form, because it's essentially taken one variable, because, okay? And then when you take product of this, you will also get a completely monotone function. That's why p to the power minus alpha, in this case, is completely monotone for any alpha positive. Okay. And we want to write down the explicit representation of its inverse power. So we want to get a formula for the Riesz kernel of this function. And the theorem is as follows. So we suppose, like, let me fix, so my x lives in Rn, so it's n dimensional vector, and let me fix n last linear forms to be coordinates. So I take L m minus n n minus n plus 1 plus I to be i's unit vector from 1 to n. Okay. So, like, in particular, my form is divisible by each coordinate. Okay. My product of linear forms contains x1, etc., xn. And so the first m minus n forms are any. Okay, then p to the power minus alpha of x admits the following representation. It's an integral on the on the cone C star, which is in this case a polyhedral cone because p is defined by linear form, so it's a polyhedral cone. My hyperbolistic cone is polyhedral. And my Riesz kernel is going by the function that is called Gelfand-Armoto hypergeometric function. And I will try to explain what it is now. So it will be a function that depends in a very complicated way on parameters.
But this is for product of linear forms.
Yes, this is for product of linear. So,
I'm with you.
sorry?
I'm with you. Okay.
Okay. This is for product, yes, exactly. I'm considering only product of linear forms. And this function, it is called Gelfand-Armoto hypergeometric function, is a classical, kind of classical object. And, okay, so let me start with any matrix of size k times m. Okay.
Is this case interesting in general, product of linear forms?
For what?
I mean, this is kind of a very special case of your
Of course, right.
illustration.
Yes, so it has, so, okay, it's interesting because it has lots of connections to combinatorics. Because this function, they play a very important role in combinatorics. And if time permitting, I will maybe, I have just 10 minutes, right?
But
So I don't.
The geometric story is completely different.
Yeah, no, okay, I will. So let me take k by m matrix of maximal rank, such that A is of this kind. It has first minor, which is identity minor, and some sum enters here. Okay, and let me take any m many complex numbers, such that they sum up to m minus k. Okay? And then the hypergeometric function that depends on beta, on this vector of parameters, and my matrix A is defined as follows. It's the integral of products of linear forms sorry. N minus k and plus 1 n. So my matrix A has k many rows, right? So these k rows, they define k many linear forms. I take the linear forms that are defined by these rows, and I take the positive part of it and take them to the power bj minus 1. And I integrate against some differential form over the unit sphere in my space Rk. So this S is a unit sphere in my space Rk. In fact, it doesn't matter what surface I take. It should be just encircling the origin and intersect each row once. So for example, a sphere. And omega of x is a differential form that is just so it's a differential form of order k minus 1. So this is a hypersurface of dimension minus m minus 1, k minus 1. And so I can integrate k minus 1 form over a hypersurface in Rk, and I get an answer and some number, which is a function of a and b. So this is called Gelfand-Talmothe hypergeometric function. And the function that I wrote here is just, let me call this psi tilde. So psi tilde of alpha Ly is just by definition psi of beta and Al of y, where beta is the following vector of exponents. So it takes, as a first place, it takes n minus m alpha, okay, and then it is filled with alphas, and a alpha of y is a matrix that has first minor to be fixed, and here it has minus y, minus L1, minus Ln. Sorry, actually here I don't have minus. So it's very special. So in fact, you make sure that it's matrix of size, actually. So it's a matrix of this kind, okay? Doesn't matter what size it has. And yes, and this is a formula for the Riesz kernel that is associated to the product of linear forms. Let me just briefly mention why it is interesting. So for example, you can, for some special values of this function, of this Riesz kernel, you can get some functions that appear in combinatorics. For example, let me take alpha to be 1. So I'm interested in complete monotonicity of function reciprocal of products of linear forms. Okay? In this case, so I know that it's completely monotone. And in this case, my Riesz kernel, so when alpha is 1, has the following interpretation. I need to integrate. I consider a linear map from Rm to Rn that sends i's unit vector here into Li, one of my vectors that I picked here. Okay. So it's a linear form. It is a projection from higher dimensional space to Rn. And I need to integrate over the fibers of this linear map intersected with a positive foursome in Rm. In fact, if you assume that your hyperbolicity cone defined by these linear forms is pointed, these fibers will be compact polyhedra. So in general, it's a non-compact polyhedra, but under the condition that hyperbolicity cone is pointed, the polyhedral cone is pointed, this will be a compact polyhedra. And you integrate, essentially, you integrate the volume, you take just the volume of your polyhedron with respect to the back measure on, so let me take variable z here, and I take dz, and I need to normalize by the Gramian of this linear transformation. So I need to divide by determinant of G transpose. Okay, so you just integrate, you compute volume that varies as a function of y. So you have, so your hyperbolicity cone C is just, for example, let me draw a two-dimensional picture. So this is your C, okay? Then you have C duo, which is your hyperbolicity cone, which is also polyhedral. And I pick now point here in y, I pick y here, okay? And now what is the value of my Riesz kernel at this point? I just need to compute the volume with respect to the back measure up to this normalization, which is constant for all points, so it doesn't depend on the points I pick. I just need to compute the volume of this polyhedra. And this, people like that know combinatorics, maybe they have encountered a discrete analog of this function. Some people call it volume function. And in fact, it is a piecewise polynomial function. So it's not just continuous as we expect from general theory, but it's actually piecewise polynomial. And piecewise polynomiality breaks exactly.
Like a spline.
Sorry?
Like a spline.
Yes, it's like yes, it's like a spline, exactly. But piecewise what is interesting, it has piecewise polynomiality brings when y becomes dependent with some hyperplanes defined by my linear forms. Okay, when we cross, so you can imagine what is a combinatorial chamber decomposition of my C star defined by linear forms. Okay, so in the two-dimensional case, for example, if I have three linear forms, then my C star is just positive span of these vectors, and these three vectors look like this. So when my y is here, varies in this region, everything is good, everything is polynomial. Also here, everything is polynomial, but when I cross the boundary, the polynomiality breaks down. It remains continuous, but the function changes. And yes, and this might, I don't know. So we try to find more nice interpretations of these functions. And yeah, I don't have time to talk about so what is known for elementary symmetric polynomial, but let me just say that for elementary symmetric polynomial, as I mentioned, this conjecture that was on this blackboard, it was settled, and moreover, there is another conjecture that is due to Scott and Sokol that says the following. So this is a conjecture as well. So far, by now it's half of the conjecture, half of it is proved. So elementary symmetric polynomial that I denote by EMN, when I take alpha power of it, it is completely monotone on positive orthant if and only if alpha is either 0 or greater than n minus m over 2. And in fact, this direction is settled. And it will also appear in the forthcoming paper. And the other direction is open. But we know that for some alpha, so we know that sufficiently big alpha ensures complete monotonicity of this function, but the conjecture is that it works for any alpha in this range. In fact, it should be strictly positive. Okay, thank you very much.
Questions, comments? John?
The formula that you get for the determinant of alpha.
Okay.
that it really lacks the flavor of a log barrier function. Of course,
Exactly.
right?
I don't know much about that, but yes, it's true.
A universal barrier would be something on this form, except you don't have a density. You just have the trace, exponential of the trace, right?
Yes.
The determinant of a to the power minus 1 would be a barrier for...
Without this piece.
yeah.
Okay.
So a universal barrier is defined as this Laplace transform.
Exactly. This is all. Yes, I didn't say, but I didn't want to throw in too many terms. But this transformation that defines this inverse power is called Laplace transform.
So can you comment about this, the definition of the universal barrier function? As
Actually, I'm not prepared to talk about that. So, but I expect there is some connection. Okay.
So,
Do you think there's any hope of extending this conjecture to like SOS hyperbolic polynomials? I think the elementary symmetric ones are SOS
ISS
hyperbolic. Is that true,
Not
James?
sure.
Oh,
Some
okay.
of them, yes, I know, but I'm not sure.
You mean the conjecture of Scott and Sokol?
This sort of integral being non-negative on the cone or dual cone.
Well, but
The
this conjecture holds for all. So conjecturally, this holds for all hyperbolic polynomials.
Yeah. Okay.
Exactly,
So-
and actually, it's also necessary. So, like Bernd asked, I think, like whether it holds for log concave or Lorentzian polynomials, but this cannot. So, like the class is only is inside hyperbolic polynomials for which it holds. Because I mentioned already in the beginning that if this representation exists with positive measures, then your polynomial must be hyperbolic.
It would be interesting to try for simple square, like if one assumed some sort of representation, maybe not like a power determinant, but
So, like, let me mention, maybe it will be interesting to combinatorists, that some natural stable polynomials that come from graph theory, like for example spanning tree polynomials for series parallel graphs, they actually were. So for these polynomials, it also holds that some inverse power of it is completely monotone, and some of these exponents were listed in the same paper where this conjecture was stated. So if you're interested, you can look it up. So like for some combinatorially defined stable polynomials, you can say something using like some tools that are not
But they are
analytic.
determinantals.
Sorry?
They are determinantals.
Are they all determinantal?
Yeah,
Okay, then
except for the elementary
for the elementary symmetric. Okay, but elementary symmetric polynomials, they not all of them correspond to this spanning tree polynomials of series parallel graph, right?
No, they don't.
Okay.
They don't at all.
But yes, and this question, which I asked in the beginning, seems to be very interesting, like whether there exists a determinantal representation of some power of elementary symmetric polynomial. And of course, due to Peter's result, it's not interesting. Like, if you want to say something about the cone, but like if you want to be algebraic, then it might be interesting. Yes.
Are there conjectures concerning effective bounds on how large the alpha should be?
Yeah, there are no conjectures, but in fact, my personal belief would be that if there exists one alpha, then there exists such alpha such that all alpha beyond work. But I don't know. At least in all known cases, it holds.
so what's the connection between these things and somehow partition functions? I mean, because in here these are...
Okay, right, exactly. So this like the motivation, I think one of the motivation was to construct so-called hyperbolic exponential families, and then they correspond to partition function of probability distribution. So this is, like you mentioned, this is a Wishart distribution, and this, like the product of linear forms, maybe you can say something about your probability distribution in your family, in your polyhedral family, let's say, using some properties of hyperbolic polynomials. So for example, these functions, they admit nice description in terms of differential operators. So you can go on the dual side and ask which differential operators kill this function. And there is a rich theory developed, yeah. So for example, people study this approach, and this ideal in the ring of differential operator, and then they. Okay.
So one question is, so it's trivial for it's trivial for the product x1 times x2 times x.
Exactly. It's trivial.
And then if you take directional derivatives on that, you get the elementary symmetric.
Exactly. Well, no. Oh,
Do you know if?
now, if you get directional derivatives of products of coordinates, you get the elementary symmetrical. But you need to be careful because you cannot exchange the derivative with a
Power.
with a power.
No, yeah, I know. But my question is, can you? Maybe there's a theorem that says that if you have a Riesz kernel for h and some alpha, then you also have it for.
No, I was thinking about that, and there is not such a theorem.
No, it's not. There could be something.
There could be, but
It's not obvious.
it's not obvious, and yeah, exactly, that's not obvious.
That
And
could be one way of sort of.
yes, it could be one way, exactly. That was one of our thoughts, but we were not able to say something.
There's no other questions or comments. We'll thank the speaker again.